people to get on the webinar, and then we'll get started. So just hold tight. 3 minutes after the hour, so I think that's going to be enough time for us to get started, and I'm sure some other people will join us along the way. Thanks so much for everyone for participating in this webinar from the Concrete Sustainability Hub. My name is Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub. And I'm going to talk to you about our pavements-related research today. At our last webinar, a few weeks ago, we talked about our buildings-related research, and if you missed that one and are interested, we have a posting on our website of where you can get a link to the video for that. Because of the number of people that we have on, we have everyone muted, and so if you have questions that you'd like to ask, there's a chat window that you can use within WebEx, and so please, by all means, put in your questions along the way, and then when we get to the end of the presentation, I'll answer those and any other ones that you generate along the way. So, for those of you who are not familiar with the Concrete Sustainability Hub, we've been around for about 7 years or so, and we are jointly funded by the Portland Cement Association and the Ready Mix Concrete Research and Education Foundation. And our research in pavements and sustainability is motivated by a couple of different topics. One of them, is that the U.S. isn't sufficiently investing in its road system, and I'm sure a lot of us hear about the poor condition of our road system, and also that there are significant funds that are required to improve it. And we add to this the challenge that insufficient investments are being made in the road system. And so as a consequence, we have this challenge of how do we deal with our deteriorating road system within an environment of limited funds. To add to that, governments are being forced to do more with less because there are less revenues that are available. This is showing a chart from a New York Times article from a few years ago that was showing states and what their gasoline tax is, and most states, their gasoline tax is fixed. It's not tied to inflation. And as a consequence, as inflation increases, the amount of revenue that they get effectively decreases, particularly when we add to the fact that cars are becoming more fuel efficient as well. And that's why you see kind of a turn down in the curve in terms of the amount of revenues that are available to governments to deal with this. So that just adds to the financial pressure that governments are dealing with. Another element in this environment is that the FHWA has issued new performance management rules due to the MAP 21, or Moving Ahead for Progress in the 21st Century legislation that was passed a few years ago. FHWA just recently issued new rules about what transportation agencies need to do in terms of their asset management plans. And so there are several measures related to tracking the conditions and setting targets, but some of the ones that we're particularly interested in are related to what are they going to do for risk analysis, life cycle planning, and what are some of their investment strategies. And that's all, I think, related to getting the most out of the investment dollars that we have. So, and actually, DOTs are thinking about this a lot now because they have to submit initial plans for how they're going to meet some of these rules by next April. So. Another element that plays into this is that, there are a lot of questions about pavements' impact on the environment, whether it be about climate change or air quality. They're interested in pavements and also the vehicles that are driving on the pavements. And also, urban heat islands is another big topic, and people are interested in how the pavements that are in our cities may or may not be contributing to those issues. So. The research that we're trying to do in a Concrete Sustainability Hub is meant to really support sustainable infrastructure design decisions, and we see that infrastructure achieved by a balance of a couple different factors. One, to do this, you need to increase the performance of the pavement or whatever type of structure that you're interested in. Two, you need to reduce costs, and three, reduce environmental impacts. That's how we really get the most bang for our buck. But what's challenging about this is that you really need to analyze and balance trade-offs in these three different areas. And there's a couple different techniques you can use, like to reduce the performance. What you want to do is use the design process to be able to do that, whereas to reduce cost, a method I'm going to be talking about, lifecycle cost analysis, can be done for that, and reducing environmental impacts, you can use lifecycle assessment. So all those things need to be looked at together, and that's something that we try and do in the hub. Our mission is to develop breakthroughs that lead to more sustainable and durable infrastructure, buildings, and homes, and we do that with a three-pronged strategy. One is providing a scientific basis for informed decisions. Two, demonstrating the benefits of a life cycle perspective, and three, transferring research into practice. And some of those will be themes throughout what I'm going to be talking about today. But I think a unique element of our team is that our approach is holistic and multidisciplinary. We have people who specialize in material science and what is happening in cement and concrete at a very small scale, people who specialize in engineering related to pavements or building, and people look at economic and environmental issues as well. So we try to look at all those things together in order to be able to support those sustainable design decisions. Our pavement research goals really are trying to drive the pervasive use of life cycle costing and life cycle assessment for pavement design, pavement type selection, maintenance decisions, and asset management. I think that long-term perspective is really important in all those areas. But when you take that long-term perspective, it's important to have a robust decision-making process. And by robust meaning that you're confident in the results despite basically any types of uncertainty or risk that you may run into. So going back to these different topics that we have, these are showing some of our different research topics down here that fall within these different buckets. And then these topics also fall into, some of them are more related to specific pavement projects, and some of them are more related to pavement networks. So we have some research that's being done on the durability of concrete pavements that's really heavily on the science side, but also involves some engineering. We also have some research looking at the environmental impact of pavement albedo, which is related to the reflectivity of the pavements. That's also heavily involved in science and some engineering as well. We have some research on pavement vehicle interaction, which has to do with the rolling resistance of the vehicles on the pavements, and I'll talk about that. That's pretty much in the engineering bucket. And then there's several topics on the economics and environmental side as well. Life cycle cost analysis is really geared towards individual projects, as is life cycle assessment. But there are also some network analyses that can be done as well, and I'll be talking about some work that we have to look at how you allocate funds across different pavement projects, and also some network analyses that can be done of pavement vehicle interaction. I'm also going to be talking about some work we've done looking at inter-industry competition, which kind of falls in between those that network and project scale. But what you'll probably notice about all these is that they really are representative of that balance that I mentioned we need to have between analyzing performance, cost, and environmental impacts. And basically, these topics over here are mostly about performance, whereas we have quite a few about cost and environmental impacts. And that's because we think those really have to be viewed together. What I'm going to be talking about first is basically our projects that are more our research that's more in this project level scale, so this pavement vehicle interaction, life cycle cost analysis, and life cycle assessment. And then in the second half, I'll get more into some of these network related analyses and leave the durability and albedo for their own presentations at a future webinar. So. All right, so on the life cycle side of these things for particular projects, this life cycle perspective is really important for the work that we're doing. And the reason is that there are multiple mechanisms for reducing environmental impact and cost, right? One can improve materials production by using recycled content or reducing energy associated with that, improving material performance. One can also design or construct pavements so that they use less material, perhaps by using stronger material or creating longer lasting designs. You can also design them so that they reduce the amount of vehicle fuel consumption or heat island effects and enable material recovery at end of life. The key thing is that, any one of these different strategies could have implications on the rest of them, and their significance also needs to be compared. So to really prioritize which of these mechanisms is going to be most important requires a trade-off analysis of performance and life cycle environmental impacts and costs. You really need to see that in the whole life cycle perspective. I mentioned one of the approaches that we use particularly to look at cost is LCCA, or Life Cycle Cost Analysis. This is a method for evaluating the total cost of ownership. So what we can do is compare a couple different alternatives, in this case alternative A and alternative B, and look at their costs associated with initial construction, and then look at costs associated with rehabilitation in the future, right? And so then what we can do is combine those into a total life cycle cost. So even though alternative A had a higher initial cost, it had lower life cycle costs. So that's our whole approach. Look, how do we quantify those total costs of ownership? Life cycle assessment is similar in that it tries to look at the total life cycle effects of a product or a process, but in this case we're looking at quantifying environmental impact, or like the footprint. And if each of these boxes right here represent processes that occur in a life cycle. So for example, this could be digging limestone out of the earth and then transforming that into cement and then making that into concrete, and then laying it in a pavement, and then throughout the use phase. So within each of those processes, what we do is we quantify the energy and raw material inputs, and then emissions to air, land, and water. And so we can do that for the entire life cycle to get the overall environmental footprint for whatever our metric is that's of interest. Now, these processes can be and have been used for pavements, but a big motivation for us is thinking about how you can integrate these into the design process. And the issue is that pavement design is iterative. If we talk about a general design process, what will usually happen is that there's a design proposal based on a particular context. So what the kind of traffic is, what the climate is, what the soil conditions are. We start with that initial design proposal, and then what's increasingly happening is that design is analyzed using mechanistic empirical design principles. So we check with that design, does it meet our performance requirements? Does it last for a certain number of years? And if not, then we might iterate and make some tweaks, making it thicker, changing some of the materials, whatever it is, until we come out with a final design. What currently happens now is that if you're going to do a life cycle assessment or a life cycle cost analysis, you take that final design and develop what we call a bill of activities, which is basically all the details that we need, the inputs to do that LCA and LCCA. So as a consequence, when we do that type of analysis, we don't have any opportunity to change the design, right? There's a disconnect. We're only doing analysis on a final design. Instead, what we'd like to see is that each time you analyze the design, not only do you analyze its performance requirements, you also analyze its cost and environmental impacts as well, and then can iterate on all of these three things together, and therefore your final design is kind of an optimization of all of those things together. So what we're trying to do is to be able to integrate these three different things within our project level analysis. So what I'm going to do is talk about some of the key accomplishments from our work in this cost and environmental impact space, and then shift to some of our key findings. So one of the things that we've done in this space is to create a linkage between design tools and evaluation. So, you know, we used a Pavement ME software to get outputs that can then be direct inputs for generating this bill of activities that would allow us to then do LCAs and LCCAs. So, so basically we have it as kind of an add-in to that software that can then be used in a coupled fashion to look at all these things together. The other thing that we've done is develop some models that can be used to calculate excess fuel consumption of vehicles due to pavement design and maintenance. What we're looking at here is what I mentioned earlier, this pavement-vehicle interaction. And this is essentially a measure of the rolling resistance of vehicles driving on pavements. And there's a couple different elements that we quantify. One is deflection, and that's related to the weight of the vehicle and how much of an indentation that then creates into the pavement. And so the more of an indentation there is, the more it's like the vehicle is continuously driving uphill. The other mechanism is roughness, and this is associated with, you know, how bumpy the surface is. And the more bumpy it is, the more energy that has to be absorbed by and dissipated by the shock system in the vehicle. And so both of these create excess fuel consumption. And what I mean by that is, you know, there's a certain amount of fuel that's associated with a vehicle driving on a, you know, perfectly rigid or perfectly smooth pavement, and we're quantifying that additional amount of excess fuel consumption. So there are some existing models that are available that we use to quantify this, but we spent quite a bit of time developing our own quantitative models for deflection. And what we do is we use all those sets of models to quantify the amount of deflection and roughness for a given pavement. Then we can quantify excess fuel consumption, and then from that we can look at economic and environmental impacts of this excess fuel consumption. So for any individual vehicle, this may not be a particularly big deal, but when you multiply this excess fuel consumption across all the vehicles that drive on pavements, it can be significant. So the other thing that we've done is created probabilistic life cycle cost and environmental impact models. So by probabilistic, I mean we're accounting for uncertainty. So we account for uncertainty in initial and future costs, in the environmental impact associated with these types of activities, material quantities, pavement deterioration, excess fuel consumption. So all those things we account for uncertainty, and we do it across the entire life cycle. So looking at materials, construction, maintenance, and end of life, and then also adding in this use phase of the pavement. So things that are not directly about the materials or the construction, but are more what are the impacts of these materials. And so that's a little bit more of a recent development within the community of researchers who do this type of work, but it includes that excess fuel consumption I mentioned, and also albedo and a couple other things as well. So we quantify those things. And then what we wanted to do was to basically see how significant these factors were across a range of different contexts. And so we conducted life cycle cost analyses and life cycle assessments for a wide range of scenarios, in particular in these 4 different locations that had different climates. And then we also looked at different traffic levels, and a couple other things associated with the framing conditions, the different types of pavement designs or maintenance schedules, and a couple other elements there. So I'm going to shift gears now and tell you what we found based on some of the work that we've done in this space. And just to summarize some of the key findings from our work in life cycle cost analysis and life cycle assessment. One is that this life cycle perspective matters. It's really important. Another is that pavement-vehicle interaction matters, and it can be significant. 3, the context really matters and can really influence your outcomes. And 4, risk matters, and it's really beneficial to take that risk perspective. So let me talk about each one and demonstrate what I mean by that. So, oops, for some reason my labels weren't coming up there. Let me try again. What this is showing, and I'm not sure why those are not showing up, but basically what I'm going to do is close out really quick and try that again. Maybe lost some memory. But basically what we see from the research that we've done in this space, that this life cycle perspective is really important. And there we go, that's much better. What this is showing right here is basically total life cycle costs for a state highway in Florida. And there's some details on it down here, but basically what you can see is that initial construction costs are about 47% of the total life cycle cost, but the future maintenance and rehabilitation costs are 53%. So, you know, making your decision based on these total life cycle costs is really important, because that can be over half of the total. So. The other thing is that from an environmental impact perspective, that use phase can be significant and even more than what we saw in cost. This is showing here life cycle greenhouse gas emissions of an urban interstate pavement in Missouri. What you can see is the impacts associated with materials and construction are about a third, maintenance and rehabilitation are about 7%, end of life 6%, but that use phase is you know, almost 60%. And when we take a dive into that use phase, you know, looking at, this was the total, looking into that right there, what we see is that excess fuel consumption, either due to deflection or roughness, are, you know, the largest contributors to that. And so, at least when it comes to greenhouse gas emissions, which is what I'm showing here, that PVI really matters. And we have different scenarios where we can see where roughness matters more, deflection matters more, but that's, you know, an interesting conclusion, at least, that this use phase can be such a big driver. The other thing that we find when we look at the context of these different analyses is that the context really matters, and cost can vary with location, traffic level, and pavement design. This is showing a rigid pavement design for an interstate in Colorado. What you can see is that you know, initial costs really dominate there, whereas when we look at a local highway and a rigid design, then the rehabilitation costs become a little bit more significant. We contrast that with the state highway and a flexible design. That was the example that I showed earlier, where the rehabilitation costs were a pretty significant deal, whereas the flexible design for an interstate, the rehabilitation costs are less significant. So all this is to say, you know, I'm not really getting into what are the totals and how do they compare. It's mostly just that what are your cost drivers are going to really depend on your design, your traffic level, and your location. So it's hard to draw generalities from that. When it comes to greenhouse gas emissions and how those vary, the context also matters right here. And so what I'm showing here are initial impacts, which is basically about materials and construction, rehabilitation is maintenance rehabilitation, and then end of life is right here. And what you can see in this example, again, for interstate with a rigid design, you know, the use phase is about 57% here. Rehabilitation is pretty small. But then when we go to a local highway with a rigid design, the use phase decreases. And that's primarily because you have less truck traffic and less traffic overall on that local highway. When we go to look at a state highway, we see with a flexible design, we see just a different breakdown here, with rehabilitation being a bit more. And we compare that state highway with an interstate, where we see the use phase increase again, where basically you have that higher levels of traffic, and particularly truck traffic. So once again, all this is to say it's hard to draw generalities about this, because the context really matters and should be really analyzed in any type of comparison like this. So my last point in this space is that risk really matters. And one of the benefits of using that probabilistic approach is that we can look basically at the impact of different levels of uncertainty. And this is showing the outcomes of a life cycle cost analysis. So I have life cycle costs on this axis here, and these are called cumulative distribution functions, or CDFs. And this shows the cumulative probability that we get a particular result. And so this shows it for two different designs. And so how you look at these is that, for example, you could say I have 50% confidence based on the uncertainty that these two designs will have a life cycle cost of, about what, $3.1 or $3.2 million per mile. And so at 50% confidence level, they're about the same. Maybe design 1 is a little bit less than design 2. However, if we took a 90% confidence result, which is often what engineers use when they're looking at design parameters, there's a much bigger difference, about 12%. And here we see design 2 is now lower than design 1. Another way that we can look at this is that we can say, what's the risk of exceeding a particular cost? What's our risk of exceeding, like, say, $4 million per mile? So what you can see is that in design 2, it's about 1%, and in design 1, it's about 9%. So particularly when we're talking about assets such as pavements that last for decades, we think that incorporating that risk is really important. All right, so just to summarize these key findings from our life cycle assessment, life cycle cost analysis research, this life cycle perspective really matters when making decisions about these pavements. PVI matters and can be significant. The context really matters, and risk matters, okay? What I'm going to do now is shift gears and talk about more of the network-related research that we've been doing. First, some economic analyses about inter-industry competition, and then also some network analyses related to allocation and network PVI. Okay, what are the key findings from these network-related analyses? One, we found that viable competition is really an opportunity. 2, PVI data can be used in network pavement management. And 3, diversity of maintenance, rehabilitation, and reconstruction alternatives is a means to enhance the network performance. So let me dive into each one of those, starting with the competition analysis. And our question here, it was basically, does the presence of competition between material substitutes impact pavement material prices? And there's a couple of different types of competition that you can think about in any economic environment. Intra-industry competition would basically be, if there are several bidders for a project for using the same type of technology, you could say there's a lot of competition there within those same that same industry. There'll be intra-industry competition. Inter-industry competition would be about more between material substitutes. So obviously in paving here, that inter-industry competition is more about concrete and asphalt. But more broadly, we're interested in is basically what factors are driving costs. And the way that we analyzed that is we did some statistical analyses of the Oman bid tabs database, which includes, and we looked at 10 years of data across 47 states, which ended up being about 300,000 pay items across 164,000 jobs. And we looked at basically how do these different parameters here affect prices, and can we generate a model to be able to explain prices based on these different factors. So we looked, for example, at how does the quantity of a job affect these prices, how much does annual spending in the state affect material prices, number of bidders, a whole bunch of different factors. And this last one here, basically the share of spending on asphalt or concrete in the state, we just viewed that as a proxy for inter-industry competition. And what this chart is showing here is basically across many different states, what's the 10-year average spending on concrete. And so you can see it varies from close to 0 to up to about 30% across all those 10 years. So we did these statistical analyses and developed some statistical models to be able to say, which of these factors contribute most to the prices. And so here's what we found is that when it comes to our statistical analysis for concrete initial prices, these are the different factors, and this column here with the dollar sign shows how significant that it is. So more dollar signs means that it's more significant of an impact on these concrete initial prices. And so what we found, no big surprise here, what these triangles mean is that basically if you increase the amount of volume of concrete on a job, then it decreases the price of concrete, right? So that's just economies of scale that we would expect. There's a couple of other things that we see here. Basically, the one, though, that I was talking about with competition, what we found is that, the share of spending in that state on concrete, the more that you spend on concrete, the lower the prices are. And this had a, reasonably significant effect on those results. We look at asphalt prices, similarly, like what we showed, is that the mass of asphalt on the job, the more you have of that, the more that decreases the price, and that was pretty significant. One of the interesting things, though, is that we also found that, the more that you spend on concrete in the state, the more that it decreases the asphalt prices as well. So, the conclusion that we have is that there are many different factors that can affect prices, and this is a statistical analysis, but it does seem like that competition among different industries is an opportunity to lower prices. So, moving on to the next topic here about quantifying pavement vehicle interaction. In network analyses, I demonstrated before about how we can use that PVI to quantify impacts on the environmental impacts for a particular segment, but we've also done that across pavement networks. And what this is showing right here is an estimate of excess fuel consumption from PVI in U.S. pavement test sections. So this isn't the whole pavement network in the U.S. It's just basically test sections that are managed as part of an FHWA effort called the Long-Term Pavement Performance Database. So it basically has several test sections in each state, so they monitor those pavement performance. What we could do is calculate excess fuel consumption on those segments for a variety of different types of pavements. And this is for 1 year, and what it shows is about 700 million gallons of excess fuel in 1 year. And so once again, going back to my statement that, for any given vehicle, this PVI may only be a few %, but when we look at an entire network, it can be much more significant. So what we've done is also applied those to excess fuel consumption analyses in different networks. This is showing an analysis that we did for the Virginia interstate pavement network. And what we could do is, based on data that we got from the state, we could calculate excess fuel consumption due to PVI for cars and trucks on those interstates. And green segments here have relatively low excess fuel consumption, where red is significantly higher. And what you can see is that, on the areas, particularly urban areas where you get a lot higher traffic, you have more excess fuel consumption, but that's a combination of the amount of traffic you have, but also the state of the road. So, doing a deeper dive allows you to see which of those is the bigger factor. So, and you can do a combination of those different things. So that's just showing excess fuel consumption. We took this a step further and also did analysis with California's pavement network, and looked at, not just calculating excess fuel consumption, but also then greenhouse gas emissions, and also metrics related to air quality as well. So you can use this basically to, make a case that the way that we design and maintain our pavements has these real effects. And, another thing we can calculate as well is dollars. How much are people spending on that excess fuel consumption. One of the neat things we're able to do with Caltrans, they can provide us with the total footprint of vehicles that drive over the roads in California, and that was provided by the California Air Resources Board. And then from that, we could calculate the contribution of PVI to that total footprint. It ranges here from 0.5% to 4.5% or so. And so the significance, it can be interpreted in different ways, but, one way to think about it is that in order to decrease this footprint, you either have to make significant changes on the vehicles that are driving on the roads, the amount of fuel that they consume, or you change driver behavior, or in this case, the other thing you can do is basically change some of the practices of the transportation agency. So on the one hand, changing vehicles and their consumers, you're dealing with millions of people, whereas the transportation agency, a couple hundred or maybe, 1,000 people or so. So it's a different scale in terms of what kind of effect that you can have. So. The last topic that I'm going to talk about is basically network analyses, where you take something like this, which is just a snapshot of a current condition in 1 year, and then basically be able to predict into the future what would happen if you took different type of practices. And so this is about asset management. And the goal of our pavement management research in this space is to develop decision support tools that consider project-level decisions, uncertainty and risk, and large-scale problems with long analysis periods and a diverse set of maintenance, rehabilitation, and construction alternatives. And this kind of goes back to the FHWA rules that I mentioned at the beginning about how do you make asset management decisions. So one component to that is collecting data on the performance of your system, but then the next component is how do you use that data to then make decisions about how you're going to allocate your funds. So we've developed a network allocation model that basically takes in a couple different elements. One, it takes in the current condition of the system. So kind of like I was showing with the PVI analyses, you have to understand what type of roads that you have, and then what's the deterioration rate of them. Then project models of what happens in the future. And we do this for a couple different elements. We project what prices will be in the future and can capture uncertainty in that, and also pavement deterioration, and we can capture uncertainty in that as well. So when you combine that with a set of objectives or goals, that can go into this, a literal black box here, which basically involves some optimization algorithms. And we've developed some that are pretty efficient that allow you to then look at a diverse set of maintenance, rehabilitation, and reconstruction actions. And this is particularly important because you need to be able to say, essentially in this black box, what if I did this action? What would be the projection in the future? What if I did this one? And so it allows you to look at a whole bunch to be able to say which ones make the most sense. So from that, you can then say for each individual project, which action should be taken, and then for a given year, then track that performance used, and then simulate what happens the next year, and keep iterating this out until you've finished your analysis period. Here's an example showing some results that we did with the Virginia Interstate Network. And this is showing expected roadway expenditures over a 50-year analysis period. So we took that snapshot we had at the beginning, added this network allocation model. And what's interesting, what you can see here, blue means low expenditures per unit area, yellow means medium expenditures per unit area, and black means high. And what's interesting that you say, we give it a fixed budget of $67 million per year, which is just for these interstates. And then we thought the objective is to minimize the traffic-weighted roughness. So roughness being a measure of the performance of the pavement, and then traffic-weighted tries to accommodate for that different level of traffic on there. So what's interesting is that you see, once again, those urban areas is where you get the highest levels of investment. That's where you see a lot of the black, and at least that's where you see the most elements of these black, and that kind of makes sense. That's where you get the most traffic and arguably the most deterioration as well. What's also interesting that you see is that your allocation strategy diversifies over time. The current composition of the system is mostly asphalt with some concrete near the urban areas. But when you account for the uncertainty and how prices and the performance will evolve over time, the composition changes quite a bit. And that's where we're showing this is the fixed budget per year, and here's the composition we expect in year 50. And that just has to do with the diversification of this portfolio of assets, just like you see diversification in a stock portfolio, right? What the model accounts for is that, if one material is relatively high in a particular particular year and another material is that the price is relatively low, then you want to be able to leverage that lower price option. And undoubtedly, in a long amount of time period, basically, there will be times where that's reversed. And so this diversification allows you to improve that performance. And this is how we see that manifested. What I'm showing here is the traffic-weighted IRI over the 50-year period, and once again with the cumulative probability. What we see is that when we look at scenarios where we were able to use the diverse set of maintenance, rehabilitation, and reconstruction alternatives, we get a performance that looks like this. Whereas if we, told it only use concrete, you get a worse performance. That is, you get a higher level of your traffic-weighted IRI. You want it to be as low as possible. Or even in asphalt only, you get an even worse performance as well. So with a larger range of uncertainties. So once again, that's what we find is that basically having a diverse set of alternatives, that's the ways that you can enhance your network performance and get that biggest bang for your buck. So just a reminder of what we found. We found that viable competition is an opportunity. PBI data can be used in network pavement management, and also diversity of maintenance, rehabilitation, and reconstruction alternatives as a means to enhance network performance. So what I want to close on is that, this point that sustainable infrastructure is achieved by analyzing and balancing trade-offs among performance, costs, and environmental impacts. And, the way that you seek sustainable solutions is to optimize among these three things. And we actually have an example result of this performance optimization that's shown here in an analysis that we did that's specifically about concrete pavements and looking at a couple different actions that you can take to reduce environmental impact. So if you use white aggregates, that can increase the albedo of the pavement, the reflectivity. Doing an extra rehabilitation improves the smoothness and therefore reduces the environmental impact. Orange is end-of-life stockpiling, which increases the amount of carbonation that occurs in the concrete. Using fly ash in the concrete reduces environmental impact. Then we also did a case study looking at the use of the mechanistic empirical pavement design guide, or that Pavement-ME software that I mentioned. And the purpose behind that is to try to optimize the performance of the pavement for a particular design context. And the way that you read this chart is basically this shows the cost effectiveness of a particular alternative. Basically, compared to a conventional concrete pavement design, this is how much you would spend if it's a positive number or save on this particular action. All of them save greenhouse gas emissions or global warming potential for these different things. So the width of these bars just shows how much you would save. And what's interesting, is that some of these cost money, but they end up saving greenhouse gas emissions, whereas these two right here save money and also save greenhouse gas emissions as well. And what's interesting about that is that in this case study right here, essentially what it was is there was a sense that for this context, there's a conventional design that would commonly be used, but when you use the mechanistic empirical pavement design guide, you actually were able to design a thinner pavement that was more appropriate for that context. And so by using a thinner pavement, that's why you save money and save environmental impacts as well. So this kind of optimization process, really represents a win-win, and that's, I think, the type of things that we want to go after. So with that, I'll finish, and please, if you, I'll take some questions now, but also we have quite a bit of information that's on our website with more details on these publications and reports and summaries, and you can also always send us an email as well. So I mentioned that we have a chat window that you can use to ask questions, and so by all means, please do.
Great. And we have two questions that have come in during the presentation. The first one was back at slide 29.
Okay.
And the question is there a breakdown of flexible versus rigid in each of the 4 states presented, showing initial costs and maintenance costs over life cycle?
Let me see. In 29?
It might be the one before it showed up at 29,
okay,
but it might be that one, yeah.
Yeah. So the short answer is yes. We have done analyses where we compare designs in all of these different contexts, and we have a lot of details on the pavement designs that went into this. What we did is we had a pavement engineering firm, ARA, which is the firm that actually created or implemented MEPDG and the Pavement ME software. We had them come up with what they considered to be functionally equivalent designs for all these different contexts, including maintenance scenarios and things like that. So on our website, we have a document that's quite long that goes into the details on what are the specific pavement designs and what are the assumptions about maintenance schedules. And then we have some other reports or studies that have been published where we get into a bit more details on the cost and the environmental impact comparisons of those different designs. So if you just follow up with an email, I can point you in the right direction to where that stuff is.
Great. The second question was around slide 40 or 41. The question is, what percentage of state DOT spending on each pavement type is required to maintain healthy competition?
That's still a question I think that we're trying to ask, and gets a little bit it's tricky. The short answer is we don't really know. We don't know. And I think it's going to depend on what happens in each state. The reason why, what we did is kind of a high-level analysis here where we looked at the spending that happens across all of these states, but what we're doing is basically saying if we draw broad conclusions across what impacts the prices for all the states, this is what we're able to say. But for a particular given state, we don't really have enough information yet to be able to say, here's a particular threshold and how it matters. And I think part of that is because it will depend on what's the current context for each state and what's the degree of competition that's already there. And then you have to tease out basically how much is the competition affecting prices compared to some of these other things. So it's an interesting question. I think one will, consider to pursue if we don't have a solid answer to it right now.
Thank you. The next question is a broad question, no specific slide, but can you briefly explain the difference between a rigid and a flexible pavement design?
Sure. Those are just terms for basically talking. A rigid design is generally one that's made with concrete, or here we're using Portland cement concrete, and a flexible design is generally one that's made with an asphalt concrete design. So that's pretty much just difference. Just those are different terms for talking about a rigid design being a Portland cement concrete and a flexible one being the asphalt concrete.
Thank you. Okay, the next one is, how do you quantify the use phase? Is it different from the optimum pavement condition or the total use phase contribution?
What we do is basically in, this right here, basically what we consider to be the use phase, basically all of these elements right here, the materials, the construction, the maintenance, and end of life, those are all really focused on that materials and construction, right? So what these use phase elements are basically elements that are more about what's the broader implications of that. And so, for example, like this traffic delay one is primarily used in cost analyses, and so that's basically saying because of if there's a rehabilitation project that's going on that leads to traffic delay, you quantify the amount of time that people spend, and then basically how much that cost is, how much that costs them. Essentially, for all of these things, what you need are models that can quantify the impacts of the pavement design or maintenance on something else. So, for example, this excess fuel consumption, I mentioned how we have models of the impacts of pavement roughness and deflection on excess fuel consumption. There are models about albedo, carbonation. So you need other kinds of models to be able to do that. And once again, if you follow up with an email, I can provide you with a document that kind of goes into details on what are some of the various models that we use to be able to do that.
Great. The next question is about PVI. Does PVI have a role in user costs?
Definitely. Yeah, I didn't go into that here. I might have a backup slide. Let's see. About, it doesn't look like that I do. But the short answer is that, yes, it does. So just like what I showed right here in this life cycle cost one right here is just costs associated with initial construction costs and future maintenance and rehabilitation costs. Whereas in the life cycle environmental impact, I had this use phase portion as well. We've done that for life cycle cost as well, and calculated basically a use phase impact that's associated with costs for users due to traffic delay and also excess fuel consumption. And it's not nearly as significant as you find here in the environmental impact. Like in a case study we have for interstate in Minnesota, I think it's about like 25% are the use phase costs. But within that, it's almost entirely due to the excess fuel consumption as opposed to traffic delays. So you can definitely calculate that, and I can provide some references on calculations that we've done if you follow up. Great.
And we do have time for a few more questions, but the last one that I have in front of me at the moment is what would be the ideal time for the analysis cost life cycle? Sorry, let me reread that. What would be the ideal time for the analysis of cost life cycle of pavement, rigid versus asphalt?
Like an analysis period? Is that what?
I believe it's the timing of the life cycle cost analysis. So if you're doing an LCCA of pavement, rigid versus asphalt, what would be the ideal timing for that?
Yeah. I think that, doing it early in the design process is what's important, right? So that basically it's not like, kind of like what we talked about here, when you're in the middle of that pavement design process is when you should also be calculating cost and environmental impacts to analyze them together. So I think ultimately what we'd like is that you don't have it as a separate analysis that's done. Rather, whatever pavement design software you're using should also calculate those costs and environmental impacts. So ideally we'd like to see it happen all at the same time. We don't know of places that are doing that right now, but I think that's partially because these software tools are viewed as separate. So for example, in the US, the FHWA provides a real cost software. In many states, if they're doing LCCA, they use that as their baseline, but there's someone who basically does a separate LCCA, and ideally we think they should just be done together simultaneously.
Great, and that is all the questions I've received. If there are any other questions, please feel free to type them in the Q&A box or the chat box.
And as I mentioned, if there were specific things that you were looking for, just send us an email to this email address right here, and we'll make sure we get you those specific references. Great.
Looks like there are no more questions.
Okay. Great. Well, thanks so much, everyone. What we'll be doing in future webinars is going into a bit more details on many of these topics. So if there's something that maybe seemed to us a bit too high level, fear not. We'll probably be going into it in a bit more detail in the future. All right. Thanks so much, everyone. Thanks for joining.
Thank you.